Hello. Today we are going to learn about how derivatives can be applied to real-life scenarios. Throughout this entire course, we have learned about how to take the derivative of an equation, but derivatives can actually be used to make conclusions about scenarios in real life. In this project, experts who have been studying and observing body composition give us a data set that they collected, and we can use this data set to make assumptions about what is happening with the fetus and placenta during and after birth. The data provided for the weight of the fetus and the weight of the placenta are given as the first derivative, which can be seen in the units for y, that says grams over days instead of grams. This graph represents rate of change of the weight in the placenta. Here are both data points plotted. Notice that the line of best fit equation is the polynomial with a degree of 4. This is because their squared values are close to 1, signifying that the trend line is a good fit. Now that we have a function from the graph, we can use this to calculate the second derivative for both the weight of the fetus and the weight of the placenta. Why would we need the second derivative, though? Remember in class that we learned that the second derivative can be used to calculate the inflection points of the original graph by setting it equal to 0. This is important, because these points indicate a change in concavity, which shows where the rate changes from increasing to decreasing. This is the graph of the second derivative, of the weight of the fetus. Notice that the points that lie on 0, on the y-axis are at around 112, 284, and 429. These points are the inflection points on the original graph. Similarly, this is the graph of the second derivative, of the weight of the placenta. Notice that the points that lie on 0, on the y-axis are at around 123, 189 and 251. These points are also the inflection points on the original graph. But what does this all mean for the second derivative graph of the fetus? From 112 to 284, the function is positive, and then from 284 to 429 it is negative, so it goes from concave up to concave down on the original graph. Where it is concave up, the fetus's weight is increasing at an increasing rate, which makes sense. The fetus starts off growing at an increasing rate when it's very small, and once it reaches 284 days, the baby is still increasing, but at a decreasing rate because the fetus reached the potential size of a full-grown baby. So from there on, it is always increasing but at a decreasing rate. Now look at the second derivative graph for the placenta. From 123 days to 189 days the function is positive, and then from 189 days to 251 days, the function is negative, which means that on the original graph, it goes from concave up to concave down. Where it is concave up, the placenta's weight is increasing at an increasing rate, which makes sense. When the baby is still in the womb, the placenta is increasing at an increasing rate to feed the baby nutrients and make space for the baby. Once it reaches 189 days, which is about when the baby is born, the placenta no longer needs to increase at an increasing rate because it does not need to provide any more nutrients. Notice that the second inflection points occur at very different times, though. The fetus occurs at 284 while the placenta occurs at 189. This means that the fetus's weight is increasing at an increasing rate for a longer period than the placenta. The fetus also starts increasing at a decreasing rate much later than the placenta. This is because the placenta only needs to increase at an increasing rate at a certain point, when the fetus is very small and needs to be provided its nutrients, as well as grow in size for the fetus. But once the placenta did its job, the placenta no longer needs to increase at an increasing rate. The baby is still growing though, and can continue increasing at an increasing rate until it reaches its full potential size as a baby. Of course after that, the baby will always continue to increase, but at a decreasing rate. Using the functions from the graphs of the first derivative, we can calculate the original function for weight of the fetus and placenta by finding the antiderivative. Once we have both antiderivatives, we are not done. Remember that when calculating the antiderivative, we must account for a constant, c. That is because when you take the derivative of a function, a constant does not get accounted for because you cannot take the derivative of a constant. So when you get the antiderivative of a function, there will always be a constant. Now, we have to solve for c. The data provides us with conditions, which tells us to assume that at 112 days, a regular fetus is about 100 grams, and a regular placenta weighs 120 grams. We can use these numbers to solve for the variable c. We would plug in 112 for t for both functions and set the functions equal to 100 for the fetus, and 120 for the placenta to give us each original function. Here are the graphs of the original functions. Now, we are given information from a different study done that gives us the average volume of the placenta during pregnancy, in days, for non-exercising mothers. We can plot these points starting with time at 0, and we create a function for the data. When doing this, we get a volume at time 0 to be a negative value, which does not make sense. The volume of the placenta cannot be a negative number. The function is predicting the behavior for the given data points, without considering the real-life scenario. If we were given more data between 0 and 140 days, then the graph would show us a more accurate behavior. The inflection points of the volume and weight of placenta functions are a major part of this project because they tell us a lot about the experiment and real-life context. In order to find the inflection points of the volume of placenta function, we found the second derivative of the original function. For the weight of placenta, we were given the first derivative, and then we found the second derivative and set it equal to 0 to get the inflection points. We use the first derivative to calculate the antiderivative, and get the original function. The inflection points tell us how the volume and weight of placenta behaved before and after those inflection point times. This gives us a good idea of how the function behaves, and it allows us to conclude if this model can mimic real-life situations. The inflection points of the weight of placenta and the volume of placenta relate to each other. The volume and weight both have different rates. Each function behaved in a different way prior and after each inflection point. For both sets of data, the inflection points occur between 35 to 39 weeks. The inflection points correlate with real-life scenarios of a pregnant woman. When the fetus is growing, the weight and volume are increasing at an increasing rate. This makes sense, as the fetus is still developing and still needs the nutrition from the placenta. Around 39 weeks, the volume of placenta is increasing at a decreasing rate, but the weight of the placenta is increasing at an increasing rate. What does this mean? It simply means that the placenta is getting more dense. During 39 weeks, the baby is practically fully developed, so the intake of nutrition is not as great as when the fetus is still growing. Since the fetus is not taking as much of the volume, the nutrition is being accumulated in the placental sac, which makes the weight of the sac heavier. The last inflection point for the volume of placental graph is 275 days, which is approximately 40 weeks, and that's when women give birth. Therefore, this supports that the placenta volume should not be increasing at an increasing rate, as the baby is about to be delivered. This experiment allows students to learn more about calculus through real-life experiences. This specific data collection is reliable to use, as numerous scientists and experts contributed to this research. That means that this research is very credible. Anyways, thank you for watching.